All right, Algebra 1 students, this is 2.2. Again, same thing as 2.1. There's a lot of different things going on in this section, but they're not that hard. So here we go. We have normal distributions and normal curves. A normal distribution has the same overall shape. They're symmetric, single-peaked, and bell-shaped. So these are both different normal distributions, okay, or normal curves. Any specific normal curve is completely described by giving its mean and standard deviation. So you see how these have that same bell-shaped, single-peaked, and they're symmetric, okay? So which of the graphs has a higher standard deviation? Well, this first one, because it's wider, right? Standard deviation is a measure of the spread of the distribution. So because that this sigma standard deviation is bigger, higher standard deviation than this one. And notice that this standard deviation falls right here where it's at its steepest point. It's also called the point of inflection if you're a calc student, okay? The steepest point. So over here where it's at steepest, that's where the one standard deviation is. We abbreviate normal curves with the mean mu and the standard deviation sigma as n for normal curve, mu comma sigma. Okay? Again, mu and sigma are for population mean and standard deviation. Remember, x bar is for a sample and s of x is for the sample. We don't describe normal distributions of samples. We only describe them as populations. So here's some examples. So scores on standardized tests. Most people score around in the middle. Some people do very well, some people do not so well, but the most people are in the middle. Repeated measurement of the same quantity. If you measure the same thing every single time, it's going to be off by a little bit every single time because measurements are not necessarily going to be perfect. But most of them will be in the middle, but every once in a while you'll get a measurement that's very big or very small. IQ scores. This is the best example because most people are at an average intelligence. Some people, very few people, are at that high and very, very high intelligence, but also very few people are at that low intelligence quotient. Okay? It's a nice way of thinking about it. And then characteristics of biologic populations. So lengths of grasshoppers, heights, lots of different things. There's way more than this. There's very, very, very many things that are described by normal curves and follow that. And we'll see a lot of them in this course. So we have the empirical rule, the 68, 95, 99.7 rule. The sooner you memorize that, the easier it will be. You will use this the entire school year, mostly for estimating purposes. But approximately 68% of the observations fall within one standard deviation of the mean. So in this picture, remember that point of inflection, that steepest point is right there. So this is where one standard deviation is. 68%, so way more than half fall within one standard deviation. 95% fall within two standard deviations, so that's here and here. And 99.7, almost everything falls within three standard deviations. These little tails at the end are very, very, very small. That's only 0.3 combined. So, the batting averages for Major League Baseball players in 2009 followed a normal distribution. The mean batting average was 0.261 with a standard deviation of 0.034. I'm going to label those with the symbols. This is mu, and this is sigma. Sketch a normal density curve for this distribution of batting averages. Label the points that are 1, 2, and 3 standard deviations from the mean. You will get much better at drawing these as the year goes on. I've had a lot of practice, but it's really, really hard to draw this iPad. Okay, it doesn't have to be perfect. We're just looking for that symmetric and bell shape. So the middle of our data right here is our mean, which is 0.261. Our standard deviation 1 above and below, remember it falls at that inflection point, so that steepest point, which is about here. So we're going to add one standard deviation above the mean and one standard deviation below the mean. So 0.295 and 0.227. So that was one standard deviation. Then we're going to go the same amount to the left and the right, roughly. This will be 2 standard deviations from the mean. So that's 2 standard deviations above, 0.329, and 2 standard deviations below, 0.193. Now we'll go 3 standard deviations, so this will be our 99.7. .159 and .363. So if we want to know what percent of the batting averages are above .329, well, we know our 68, 95, 99.7% rule. So we're looking for this area here. Well, we know 95% of the data falls between these two orange pieces. So 5% is to the right and the left of here, but it's symmetric. So that means that half of 5% is over here. So this is 2.5%. What percent of the batting averages are between .227 and .295? Well, that's one standard deviation, so that's easy. One standard deviation above and below, that's 68% of the data. We're going to do some more of that in class, but hopefully you're picking this up. I just showed you how there are different normal distributions, but we're going to talk about one in particular that's the standard normal. There's only one standard normal, and this is what we use so that we can compare. Remember, we standardize things with z-scores. So the standard normal distribution has a mu of 0, a mean of 0, and a sigma or standard deviation of 1. Okay, so if we were to write it, here's our standard normal. We would call this normal 0, 1. Okay, so what percent of the area is to the left of 0? Well, 0 is our middle, so we want to know it's half of our curve, right? So that's 50%, where z is less than 0. We're not using x anymore like in the last ones, we're using z. To put that into the calculator, we go to Menu, Stats, Distribution, and then Norm CDF. Don't worry about PDF, CDF right now, just know that you're going to use CDF. It stands for Cumulative Distribution Function. Menu, Stats, Distributions, Norm CDF. Our lower bound was negative infinity. Our upper bound was 0. And then it was a standard normal, so mu 0, sigma of 1. And there it is, 0.5, which is 50%. Now we're going to use our calculator to do the rest of that, where z is less than 1.2. Now I'm going to draw a picture every single time, but I already have a picture, so I'm just going to use it. So there's 1.2 roughly, and I want the area less than 1.2. So that area. So this time we're looking at negative infinity to 1.2 with the same mu and sigma. And that's 0.88, and I'm going to round that to 5. So this is 0.885. I could say 88.5% if I wanted, but it doesn't matter. Why make it harder? Now I want to know z above negative 1.3. So there's negative 1.3 approximately. And I want to know above. So this area, that's above. So I'm going from negative 1.3 to infinity. Now again, you have to find the infinity. We'll practice this in class. Again, mine's going to look different than yours. But you have to practice the button pushing yourself. Again, This is where people get tripped up. They know how to do everything. They forget how to push the frickin' buttons. Just practice it and you'll get it. So this is 0.903. Then we want to know the area between -1 and 0.3. So I'm going to draw it on my picture. So from -1 to 0.3. Again, doesn't have to be perfect, and I want this area in the middle. This is 0.3. 0.46. And lastly, between -1 and 1, well, let's estimate it first, right? One standard deviation should be about 68% of the data, so my estimate should be 0.68, but it's not going to be perfect. That's an approximation, the empirical rule. So when we do it on our calculator, we see it's 0.682, or 683 if we round. So it's not perfect, but it works out just fine. Okay, you're just learning that the empirical rule is not perfect. So what happens when you know the area, but we're looking for the z-score? So what z-score has an area to the left of it as 0.61? So we'll draw a picture. So again, not perfect, doesn't matter, but we're at an area to the left, 0.61. Well, remember half is in the middle because that's where our mean is, and who cares? Good enough. This area is 0.61. Okay, we're looking for the z that corresponds to it. We know it has to be positive because it's bigger than 50%, right? Because we're more than half of our data to the right. Okay, so when we go back to our distributions, we're going to choose inverse norm, and we're going to fill it in with the area to the left. Keyword here is left. It does not work with the area to the right. So menu, stats, distributions, inverse normal, and the area to the left is 0.61. And we're still with our standard normal mu 0, sigma 1. That'll change later. So 0.279, our z equals 0.279, right? It's less than 1 standard deviation. That makes sense. What z-score has the area to the right of 0.23? So if we draw our picture again, we want the area to the right, 0.23. Well, remember that the whole area under the curve is 1 because this is a density curve. So we know that the area to the left has to be the opposite. This area to the left is 1 minus 0.23, which is 0.77. So when we're looking for the z-score here, we're going to use this area of 0.77 in our calculator. Or we could even just say 1 minus. I'm going to say 1 minus 0.23 because I don't even want to do any math. 0.739. So our z equals 0.739. And what is the z-score for the 73rd percentile? So I'll draw another picture. So 73% is less than the z-score, so over here-ish. This is 73%, 0.73. Okay, remember percentiles are the area below, so to the left. So we want to know this z-score. So 0.613. Assessing normality. Now this is 3 different parts to it. This is not the most important section, but this does come up on the AP test a little bit, so we want to make sure we know all 3 of these methods. Now remember when we were describing our distributions, we never said that they were normal. We can only do that if it follows these criteria, but most of the time when we describe distributions, we're just going to call this symmetric and single-peaked and bell-shaped, that sort of thing. We're not going to call them normal unless we check some more things. So the measurements below describe the usable capacity of a sample of 36 side-by-side refrigerators. So are these data close to normal? So what we need to do is we're going to take all this data and put it into our calculator. We're going to look at a graph of it. We're going to check the empirical rule, and we're going to use a normal probability plot. So we need to put all the data into the calculator. I have named fridges, and because that's about fridges, and I have all the data points in here. What you need to do is add a data and statistics page, and now we can look at the dot plot. So this dot plot doesn't show us too much. You can see that there's a lot going on in the middle here and a few things on the ends, which is good because remember, we want the majority of our data to be in the middle and then less on the ends because that's normal. But this is a little hard to see. So what we're going to do is we're going to make it into a histogram. So go menu, plot type, histogram. Now it looks better. Again, we're starting to see that shape. I'm going to cheat it a little bit. I'm going to go to menu, plot properties, and I'm going to change the bin settings to 0.8. See what that does. It's starting to look better. You see the majority of the data is in the middle. There's less on the ends. We're starting to see that bell-shaped curve come out, which is what we want. So if we were to describe the distribution, the shape is approximately bell-shaped. Okay, we could talk the outliers, center, spread, all that stuff, but I'm just looking for the shape right now. Is it reasonable to call it bell-shaped? Yeah, kinda. Yeah, again, this is the first of the very uncertain nature of statistics. Good enough is good enough for statistics, and that's what we're going for. Then we need to find the mean and the standard deviation. So we need a calculator page, and we're going to do the one variable stats. So menu, stats, stat calcs, one variable stats, and we're going to use our fridge data. So you can see our mean is 15.825. And again, it's X bar because this is a sample. We don't have all of the fridge data everywhere. So we're also going to use S of X, that 1.217. And we'll round that to 1.22. We don't want to use the sigma because we don't have all of the data. It's not a population, it's just a sample. So I wrote that down. So we have 15.825 and 1.22. We want to know what the percent of the data points are one standard deviation from the mean. So what I did is I added 1.22 to the mean to get this side, and I subtracted it, remember, one standard deviation above and below the mean. So here's my interval. So I'm looking to see which numbers fall in this interval. So 14.61, so it's a little bigger than this one, and 17.05, so these fall in it. Now I'm going to just see how many of these pieces of data fall in the middle, but I'm going to count the outsides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 are outside of my range, which means that 36 minus 12 are what's inside. So 24 out of 36 data points fall within one standard deviation. Well, that should be about 68%. 66.7. So I'll round it to 67. So 67, about 67% of the data falls within one standard deviation. That's so close to 68. That's great. Then I have two standard deviations. Well, I have two standard deviations above 115.825 and two standard deviations below. So let's see how many fall between two standard deviations. 13.38, so that captures this one, and 18.26, which captures this one. So it captures all but these last two. So 34 out of 36. So we're hoping that that's close to 95 to follow our empirical rule. So 94. So that's very close to 95. That's awesome. And then three standard deviations, again, three standard deviations above and three standard deviations below. So let's see, 12.16 and 19.48, that's all of them. So this is 100%. So does it roughly follow the empirical rule? Yes, very closely actually. Okay, the numbers could be a little more off than that. Maybe it's going to be close enough where you need to make a judgment call, and that's fine. Just defend whatever answer you go with. So that's checking the empirical rule. And then we can use a normal probability plot. A normal probability plot is similar to a scatter plot, where the x-axis is the value of the data point and the y-axis is the point's z-score. For normal distributions, the normal probability plot appears as an approximately straight diagonal line. We can make a normal probability plot on the graphing calculator, so we're going to use our fridge data to do that. So on our fridge data, you can go to any one of these. I'm going to go to Menu, Plot Type, Normal Probability Plot. And that looks very linear. So since it's following that linear pattern, we can say that the data is approximately normal. Okay, again, it doesn't have to be perfect. We're just looking for that linear pattern. If it was worse than that, then we might say something else. Again, justifying it is all you can do.